a 20 to 25 minutes for interaction with expert. Being an Indian, we should start our session with Janagana Mana on the occasion of Independence Day. I request all the participants to unmute your mic and start singing together.
Tinayaka Jaya He
तब जय गाथा जन गण मंगल दायक जय जय भारत भाग्य विधाता जय 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 Okay, thank you. Now I invite Dr. Bhargav Koradia sir, HOD EC Department, to brief about EC Department, BVM and today's expert. Welcome you, sir.
Thank you, Professor Palak. On behalf of BVM Engineering College and EC Department, I welcome you all. At the outset, I would like to greet all my fellow nation mates a very happy Independence Day. BVM Engineering College is one of the oldest engineering college in the state of Gujarat, established way back in the year 1948. Then BVM has produced engineering stalwarts in engineering categories. BVM has produced more than 21,000 engineering graduates and they are working all parts of the globe. As you know that BVM is one of the first autonomous institute in the state of Gujarat, and since 2015 BVM is working under autonomous status, which is approved by the UGC. The vision of BVM is to produce globally innovative engineers with core value, and BVM is focused in producing such quality engineers with the core value. I would like to brief about some of the achievements that BVM has recently obtained. Recently, the National Institute Ranking Framework, which is provided by MHRD, BVM is ranked amongst the top 300 engineering colleges in the nation. Apart from that, BVM is also having one of the strongest alumni support in the way that most of the alumni are associated heavily with the institution and simply visiting the institute for supporting the different activities at the institution. Talking about the EC department, EC department is established in the year 2006, and since then EC department has produced more than 11 batches at present. And since last 3 years, EC department has come up with the state-of-art center of excellence in the domain of industrial automation as well as IoT. We have, along with the EC department, we have electronics department which are working closely with the electronics and communication department. They also set up one of the center of excellence in the domain of RF and microwave. At EC department and at the college, the Saturday is always kept for learning beyond syllabus. So today we are fortunate that Saturday is mixed with our very own Independence Day. So we are fortunate to have expert from Pope Marshall. So the purpose of Saturday's activity is to enhance industry institute interaction and to allow our student and faculty members to enrich their knowledge. Today we have with us a very renowned and expert in the domain of instrumentation and control, Mr. Pratap Makwana, who is having more than 18 years of experience, out of which 13 years of experience at the Pope Marshall. He is presently heading divisional head for boiler house solutions He has having many primary responsibility, and he is handling many core projects. The most recent big projects which he has been handling in the organization are development and execution of NG LPG fire burner, boiler control system for boiler control revamp project, development of multiple hot water control system based on steam to hot water heat exchanger, artificial intelligence control strategy for BLM, fuzzy logic firing control for boiler pressure modulation, development and programming of FO, HSB, LDO fire burner and boiler control system, development and programming of CNG and LPG fire burner boiler control system, solid fuel boil control and efficiency optimization, development and programming of FO, HSB, LDO fire dual fuel burner boiler control system, development of uh, FO, HSB, LDO fire dual burner for boiler control system, and DCS based E-demand boiler control system. To his credit, he has having many awards. Few of the recent awards are he has won the national award from CII for developing ECR control, which was awarded by most innovative product in the field of energy conservation. He has also received Best Paper Award in the second international conference on fuzzy information engineering. So these are some of the important credentials of our today's expert. I welcome our today's expert, Engineer Pratap Makwana, to deliver his session.
Good morning, all. Can you see my screen, Dr. Bhargav and team?
Yes, sir.
Yes, sir.
Okay, fine. First of all, I would like to thanks to the BVM team and BVM and Dr. Bhargav's team for providing me this opportunity for the discussion on this interesting subject of the boiler instrumentation and control. So I would directly move on to what are we going to discuss today. Rather than session, I would say the discussion. So at the end of the session, we will have a good interactions on terms of what are your thoughts, what are your doubts, and how would you like to encourage yourselves in this domain. So I'm just first screens. You can see the general arrangement of a typical boiler looks complex in terms of saying at the first side, this is a solid fuel boiler, this is the oil and gas fired, this is a drum. But how the instrumentation and control plays a vital role to make it simpler, efficient, and safe operation handily. That is what we would like to cover in this session. What I'm going to cover that why we need the boiler instrumentation control, and then rest what are the controls are required to achieve the goal. So I would start first with the purpose. So the purpose of the boiler, as you know, to deliver the steam at the desired pressure. So before describing on this on further, I would like to dwell a key points which I'm going to repeat here in these sessions, and maybe many of you are aware, but the few of them may not be aware due to the interdisciplinary group, mechanical, electrical, and electronics. So these terms are basically a draft, like ID fan, FD fan. So these basically a draft, we can say that a draft can be categorized in the categorically group into two sessions. One is a natural draft. The natural draft is the draft like if we burn in our gas stove and the fumes and flames just going out through the window. It's a natural draft. Similarly, the natural draft can be said in the chimney. The chimney takes away the flue gas outlet into the atmosphere. This is the density difference between the atmosphere pressure and the flue gas pressure, which moves the flue gas outside in the atmosphere. That is a natural draft. Now, what are the forced draft? The forced draft is the draft where you are delivering the combustion air inside the furnace. Now, what is the induced draft? The induced draft is the draft which sucks the flue gas from the furnace, from the heat recovery equipment, and through the chimney. Now you balance out between FD and ID. That is called balanced draft. So the FD, ID, which said combination together as a balanced draft, can be said as a mechanical draft also. oxygen trimming, or you can say stack oxygen. So stack oxygen can be said as a combustion oxygen. So if you see in ambient, the oxygen percentage is 20.9, you can say 21%. So that is burned inside the furnace. So out in the furnace, when the combustion happening, and whatever the residue oxygen which you measure from the outlet of the furnace is called the stack oxygen. Then you can have an economizer. The economizer is the device, a heat recovery equipment, which is connected outlet of the furnace, which is recovering the heat from the flue gas to preheat the water, which again feed to the boiler through the tank. Air preheater. Air preheater is again the device for the heat recovery, where the flue gas is utilized to preheat the air which is fed inside the furnace. So these are the terms. Mechanical engineer will be aware of that, and a few of the electrical engineer will be aware of that. But for the sake of the electronic engineer people, I would like to just dwell on that, so you will catch yourself in line with the presentation. Now, the purpose of the boiler is to deliver the steam at the dry saturated pressure level. That is for the dry saturated steam. And if you want to have a higher temperature, higher velocity, then the steam is called the superheated steam, and which is required to deliver at the rated pressure and the rated temperature. So velocity will be higher and the density also will be higher in the case of superheated steam. So the more heat will be available. And in the boiler, as we see in the complex GA, you can see there are basically it divided into two categories of the cycles. One is a water cycles, water and steam drum combination together, and another is a fuel cycle. The fuel cycle is the fuel, air, draft, and chimney all put together is a fuel cycle. So in the fuel cycle can be any kind of fuel can be fired, liquid, gaseous, or solid fuel, which we'll discuss more in detail. So just an elementary model will give you the more idea about how the boiler is actually inside in the elementary point of view. So you can see in the boiler, the water cycle, which is carrying the, you can say, drum, steam drum, water tube, or water wall membrane, or combination of all of them. And the fuel cycle, as I said, fuel, air, smoke path, smoke tube, and the chimney is your fuel cycle. The purpose of the fuel and the furnace and the smoke path, first of all, the furnace is delivering the radiation, where the fuel and air is getting burned. Now, after that, the flue gas travels, and through the convection, the heat is getting transferred. So the convection, where the flue gas heat is applied to the hot water or the steams, which is becoming from the radiation energy inside the furnace, and then again it is become hot. It is getting the heat, catching the heat, and the more steam will be available with the rated pressure. Then the water. In the water, there are hard particles, the hard dissolved solids like magnesiums and calciums and potassium also, and some level the sodium also. These hard particles or hard silica level, we can say rather, is getting settled due to the makeup water, which is water we are taking whether in the form of the ground soft water or through the RO water, or we are processing something in the water side to make it more cleaner. This water is inside carrying the TDS level, and that TDS is getting settled inside the boiler drum, and we need to remove periodically by giving the blowdown into the blowdown pit. So that TDS is getting removed. That can be also improvised, because more blowdown is a more heat loss, and lesser blowdown is a harder TDS level is getting settled inside the tubes, and so more heat transfer need to be taken place and more fuel can be burned. So that is again the heat loss. Now, if we go more into detail of both the cycle, so just I would like to give the more constructive nature of the boiler. For this is a typical solid fuel boiler, where you can say it is consisting of the draft in form of ID fan, FD fan, fuel delivery through the screw feeder, which is a particularly, and screw feeder is that it's meant that it is a solid fuel boiler, and the steam drum and water wall membrane with the main bank header, with the emission control equipment. So whichever the flue gas coming out from the furnace should be cleaned enough before leaving out from the chimney to the atmosphere. That is the emission equipment. So that the back filter or electrostatic precipitors are available to have an emission control for that, and this will complete the construction of the boiler. So if in more specific point of view, if we go into the more detail, so this is your water cycle. The purpose of the water cycle is always to ensure the water pressure above the steam pressure, so that their boiler should not starve in the water demand. So always the water available to convert into the steam. And the TDS is removed through the blowdown. That is the purpose of the water cycles, and to deliver the steams from the steam drum. The purpose of the fuel cycle is to burn the fuel by mixing with the air, which is delivered through the FD fan. Fuel is burned inside the furnace, and heat is generated due to the combustion. And due to the convection, the ID fan takes away the flue gas by overcoming the resistance all across the emission, air preheater or economizer available, and the top of the furnace height, the middle of the sections. ID fans functions to carry away the flue gases outlet of the combustions and leaving out from the chimney. Now, this is a more detailed per se, the oil and gas fired boiler, which we have shown earlier also. That in oil and gas fired boiler, it's a simple in construction. We can say that it is a combination of passes. First pass is the furnace, where the radiation is taking place, where the air is getting mixed with the fuel with the help of burner. And after this flue gases passes through the second and third pass, due to the convection, heat is getting transferred. So in totality, radiation and convection zone transferring the heat to make the water into the steam, and then the flue gas is coming out from the chimney. Now, the more important, this will give you the brief idea that why we need to have a boiler instrumentation, but why we are using the steam. So the property of the steam is getting utilized to heat any process industry, like the heating applications like jacket heating, like indirect heating in terms of heat exchangers, in pharma industries and chemical industries. So the steams is when it is getting, the water is getting heated. So the water at 100 degree, the sensible heat is available at 100 degree, and then at 100 degree it vaporizes in the form of steam. So then at 100 degree it gives the 100 kilocalorie and energy available within the water, which is converted into the steams. And when you raise the pressure, so the pressure, with the help of that, it becomes denser and denser, and more heat will be available in form of latent heat. And then again giving the more heat, it will convert into the form of superheated steams and becomes in the supersonic speed, higher velocity and more density will be available. So when you take away the heat, when you utilize the heat in the form of your drying or process applications, the steam becomes the condensate and water. That steam and that condensate and water again taken back inside the tank or nearby the hot water applications, which is nearby to your process, and can be utilized in the form of again utilizing that water. So that in the way the complete cycle can be completed, so that steam, then condensate and water can be taken back. If the water is not contaminated with any chemical organics inside the process, that again it's taken back inside the tank, feed water tank, and can be reutilized. So that is the advantage of the steam getting utilized in wide way in the terms of utility for the process industry. Now, this will give you the more clear picture that when the steam pressure rises from 0 bar gauge to the 7 bar gauge, so the feed water temperature rises with the 100 degree to it becomes steam, and at 170 degree centigrade it's a steam available. So the enthalpy of steam is available in this form from this 640 kcal to kilocalorie to the 662 kilocalorie. Now this is more important, where you can say that at 0 bar gauge the volume was 1.67, it has been reduced, so means steam become denser, more denser steam. So the higher temperature, high pressure steam becomes more denser, like a bullet, like a revolver bullet, and it is very difficult to control that. And so for that we need to have a proper safety and statutory regulations available to handling the steam and combustion equipment. And that is the reason for we need to have boiler instrumentation and control. First aspect is the safety aspects, as per the combustion control and regulatory control properly tested. Then the measurement should be available such that reliable instrumentation should be placed for the proper robust controls, such that maintenance and troubleshooting can be easily available. And then we should focus on the performance side, that we can have efficient and stable control which can take care of the dynamic behavior of the boiler parameter. Just I would like to give the block diagram per se in the boiler house. So you can see the boiler house consists of boiler, which is combination of furnace, drum, and all the burners and combustors, whichever in the case of oil and gas fired boiler. Now it has heat recovery equipment if it is available. This heat recovery equipment in the form of economizer, where the flue gas temperature is getting utilized to convert the normal water. The water temperature is lesser to make it further near to the steam temperature, such that boiler can easily generate the steam with the very less fuel consumption. Then again, you can make the ambient air hotter before taking inside the furnace with the help of air preheater. And so you can see very easily what kind of instruments will be required. The instruments will be the temperature in the form of water, combustion air, and the flue gas oxygen, which is a stack oxygen, stack temperature. Then the flow in the form of steam flow, water flow, fuel flow, and the pressure and the blowdown TDS. And the all these put together, we will say that our boiler instrumentation is comprising of what is required to be controlled. So just very glimpse of the list of the components identified from that elementary model will be the most important things. Is the combustion oxygen measurement. Indirectly we can measure CO also with the help of, by maintaining the oxygen, we can control CO at some extent. Then flue gas temperature, furnace temperature, bed temperature, then feed water and combustion air temperature, level, boiler level and feed water tank level, dissolved solid to measure the silica, which is the inverse of the resistance, then the flow, steam flow, gas flow, water flow, fuel flow, and the pressure in terms of boiler pressure and the draft pressure. So now looking at this list of the instruments, we can see that all these instruments can be available in the physiological parameter in the help of transducer. So let's start with the pressure. The pressure can be measured with the help of differential pressure as well as static pressure. And to measure the pressure, the very known instruments is a strain gauge. So strain gauge is where the physiological property resistance varies with the help of deflections, where the pressure is equal to force by area, and the resistance is equal to resistivity into L by A, which you know. So resistance is proportional to the length or area in this case. So here you measure a static pressure if you block one side. So you can measure static pressure with the help of resistance change, and you can measure differential pressure also with the help of this deflection. So in both the way, this resistance change can be detected by Wheatstone bridge, which you know very well. And this Wheatstone bridge is actually the voltage difference is sensed with the instrumentation amplifier, and then it is given to the microprocessor based devices for the display. Similarly, for the differential pressure, you will have a high pressure, low pressure at the one end. Then it is differential pressure can be sensed with the help of displacement change, which is happening inside the capacitance, the plate of the capacitance. So this plate movement is varying the capacitance. So capacitance C equal to epsilon A by D. So area is here proportional to the capacitance change, and which will be detected in the form of the differential pressure transmitter, and which is very widely used to measure the differential pressure measurement to measure the orifice type of meter. And this is very widely used to measure the superheated steam basically, and water flow also, and in some cases gaseous flow also, where the gas is inert gases and it's not a clean gas, and very difficult to measure and directly take inside the very finer instruments, frequency measurement instruments. So that in that application, the DP type measurement is very widely applicable. In the DP type measurement, the orifice plate is inserted inside the flowing media, where you can see when the orifice plate is available, there will be the pressure difference, and the pressure, the lowest point of the pressure which is getting dropped is called the vena contact point, and we take the pressure difference from this point to this point, which is a differential pressure is equivalent to the flow. And this is very well defined from the Bernoulli's equations, where flow is proportional to the square root of the dP. So this device, when taking the dP, which is this dP is taken by the differential pressure transmitter, and again taken to the square root extraction device, which will convert this flow through the square root extraction will convert into the 420 milliampere, and this 420 milliampere will be proportional to the volumetric flow, or in case of mass flow also, with the correction will be applied with the density and all that. Again, to measure the hot air flow in the flue gas flow, where you want to measure the flow in meter cube per hour or kg per hour for the flue gas. So there, in that case, you can have a pitot tube also, which will be directly sensing the pressure, and this pressure will be given to the pressure transmitter, and then it will be taken into the signal conditioning device and the microprocessor, such that the display will be available proportional to the hot air flow. So another important thing is the RTD, resistance temperature detection. So RTD is very widely used to measure the temperature, can be cited as a PT100, which basically made from the platinum material. PT100 is the indication that at 0 degree temperature, 0 degree centigrade temperature, 100 ohm resistance will be available. Similarly, there are PT1000 at 0 degree centigrade, 1000 ohm resistance will be available, and this will be taken in the form of Wheatstone bridge, where the RTD is connected through the wire and will be taken in the one arm of the Wheatstone bridge, where you can this R1 into R4 equal to R3 by R2. So this, in the balance, you can have a potential difference available here, and this potential difference will be proportional to the change in resistance, which is actually the change in temperature. So RT is equal to R0 1 plus alpha delta T. So this delta T is a change which is reflected in the form of R0. Further, you can have a compensation available because the longer lead, which is a temperature element, is very far, and you have taken the wire, so you can have a compensation such that the effect of this additional resistance will be eliminated. So then it is taken as a 3-wire and can be taken as a 4-wire also. Another important temperature element for the higher temperature measurement is the thermocouple. The thermocouple is governed based on the Seebeck effect, where two dissimilar metal, when welded or joined together, and one of the end, if heated, you can get the EMF in totality from and it can be measured in the form of voltage in the millivolt form, and that we can signal condition and can define the voltage output, which is proportional to the temperature. Generally used the thermocouple is the K-type chromel alumel, and it is widely used up to the 600 degree centigrade because it's a very good linear response with the input and output. And there are other types are also that E, J, K, RST. For higher temperature, you can go with the RST type also, which are the platinum, rhodium. Another important instrument for measurement, why it is required for the combustion control, is the stake oxygen. The stake oxygen is basically governed in the principle of the Nernst equation, where the partial pressure difference, the logarithmic of the partial pressure difference, is proportional to the EMF generated at the 750 degree based on zirconia analyzer. So zirconia membrane, this is the it's acts very fine at the 750 degree temperature, and then at this temperature you can have the partial pressure, logarithmic partial pressure difference between the reference air and the flue gas air will be proportional to your stake oxygen actually leaving out from the furnace. So that will give you the indication of the stake oxygen which is leaving out from the furnace. So then we can have a better control, and it can be measured with the help of microprocessor or microcontroller based display devices, and can be PLC based device also can be display the stake oxygen. Another important flow measurement is the vortex type flow measurement, which is basically a frequency type measurement where you can have your vortex flow piezo sensor, which is inserted inside the media where we need to measure the flow, is measuring the vortices. The vortices is basically the frequency change is sensed by this pickup sensor, piezo sensor, and will be modulated this frequency change in the form of flow, in the mass flow, and as well as in the volumetric flow also. So this is very widely used for the steam, gas, and water application with the very reliable and accurately. Orifice type is having inaccuracy because with the low flow, it is very difficult to get the pressure difference. So it will not be applicable for the low flow application, but the vortex is having very high accuracy, even in the case of low flow also. So very good turn down as well as very good response available with the accurate measurement for the saturated steam application, and at 20 degrees superheat also. And for the gaseous and water, this is the best solution for measurement. Another important measurement parameter is a draft to balance for the mechanical balance draft, FD and ID. The draft pressure transmitter to be put at the 1 meter height, 800 mm to 1 meter height of the base plate. This is the boiler front door. where you can sense through the DP pressure transmitter. In this way, the DP pressure transmitter connected with the 2-core shielded cable, generally 0.5, 0.75 square mm, and it can sense the differential pressure which we need to balance out, such that ID and FD can be balanced. Now, to go more into the detail in the control per se, we would like to know somehow into the fuel properties. So we see that in the boiler, for oil fired, in case of furnace oil fired or diesel fired, or gaseous fuel like natural gas or LPG, and solid fuel like Indian coal. So we need to have the basic elements composition of the fuel are the mainly 4. One is a carbon, that is a fixed carbon, which delivers the actual heat in kilocalorie, and S percentage water, and these all 4 are called said is a part of volatile, which can easily burn. Nitrogen will not play a part in combustions. It is a combustion delimiter. Oxygen will play a role. Sulfur will not take a part. It will take the sulfur oxides. But hydrogen is a volatile which will make the combustion rate faster. So you can see from this, the oil and gas fired having a higher carbon percentage, so higher calorific value. But in case of Indian coal, you can say the carbon percentage is lesser. And also, as see that based on the fuel properties from the coal properties based on the geometry side, so the topmost layer of the coal is the lignite, which is available in India. So that's why in the topmost layer is during the screening, lot of S will be available in that, and so that's why the S percentage will be higher. Now, if we go much more deeper inside the geometry, in the coal mining, you will get the bituminous coal, sub-bituminous, and the bituminous coal will be available in the Indonesia and Australia, and having a higher calorific value. But the good part is that volatile also will be higher compared to the Indian coal. Now, so this will give you the more detail what I'm saying, that Indian coal will be having a fixed carbon, but S percentage will be higher, which is not good part. But in the Indonesian coal, the fixed carbon is higher, and similarly the volatile is also higher. S percentage is lesser, but the moisture percentage are higher because in the middle section. Now, if you go much more deeper inside the coal mining, you will get African coal, where it is having higher calorific value. So it will be having a higher carbon composition, and there will be less moisture percentage, but the S percentage will be higher. Now, all this fuel which we said is a fossil fuel because these are naturally available. Some of the fuels are need to be done some preparations also, like rice husk paddy, like wood chips, which is available, and groundnut husk in Gujarat also, coconut shell in South India side. So these are the fuels are available, but having a lesser carbon composition, but good volatile matter. So volatile will give the faster combustion rate and will help in the better combustions to deliver the heat also, but the actual heat will be lesser, calorific value will be lesser. So these are the preparatory fuel. Now, to more go into the detail in the control part and instrumentation part for the boiler per se, another question comes into mind: what are we going to do with this instrumentation control? So the better judgment is that we need to identify what is the economy of the boiler, and that economy is nothing but the boiler efficiency. So the boiler efficiency can be said as a direct efficiency. The direct efficiency is simply the percentage of the heat input which is burnt in the form of fuel, which is getting utilized to generate the heat output in the form of steam. So it simply says, which I earlier told you also, the steam output, which is the enthalpy of heat available in the form of steam, divided by the fuel and the calorific value of the fuel, will give you the direct efficiency. So you need to have a steam to fuel ratio, but the steam to fuel ratio cannot be monitored in minute or second. It need to be averaged out at least for 1 hour, or can be daily also. So that is the disadvantage of that, because it is an average value, and it also doesn't give the where are we losing, where the combustion is getting decentralized, and where are we losing in form of not having a better heat output. So for that, we need to have a detailed analysis in where are we losing in terms of losses, and these losses are sum of all losses put together and minus from 100 is the indirect efficiency for the boiler. And this indirect efficiency is composition of dry flue gas loss. All the losses comprises of dry flue gas loss, which is stack loss, moisture loss, also said as enthalpy loss, unburnt loss, which is a black smoke leaving out from the chimney, or carbon monoxide taking the heat, or carbon taken from the furnace in the form of S is also the unburnt loss or the on-off loss. All put together is your indirect efficiency available in the form of 100 minus losses. Blowdown loss cannot be said as a loss because blowdown is need to be done to remove the hard silica which is getting settled into feed water TDS, but it can be improvised. How, that we will see later. So to improvise more into the combustion control side, we need to have dry flue gas control. So in the bottom of the pyramid, we have seen that the major chunk of the loss is the stack loss, which is said as a dry flue gas loss. So the dry flue gas loss is composition of the excess air, the oxygen percentage which is leaving out from the furnace, and the higher stack temperature. So which is a combination of the ambient air which we are delivering inside the furnace is taking the taking participation in the combustion, but this ambient air is getting hotter and it is making the stack temperature hotter and leaving out from the chimney. So then this temperature is higher temperature is the loss of heat. So this difference between the stack temperature, chimney temperature, and the ambient temperature, higher the differences, higher the loss available for the dry flue gas. Even that also multiply with the excess air. So means oxygen is higher, then again it is taking more heat from the furnace, and we need to give more heat inside the furnace to heat the fuel and to generate the heat from into the water to make the steam. So again it is a more loss. What should be the percentage level for the oxygen? Typically oil fired in the tune of 3 to 3.5%, gas fired 1 to 2%, and solid fuel 5 to 8% for the oxygen. So this is the formula which I have very theoretically I have told you that delta T, the stack temperature minus ambient temperature. So ambient temperature leaving out from the chimney in the form of stack temperature, lesser the delta T and the lesser the excess air. So 21 upon 21 minus O2. So means lesser the excess air, lesser the delta T, we are minimizing in the dry flue gas loss. To give more into the detail, how to control this stack loss, we need to go slightly deeper into the combustion side. So the combustion is basically chasing for complete combustion. That's why 2C. The chasing for complete combustion is that, or without O2, we should have a combustion. But it's very tricky, very unsafe. We should have slightly oxygen should be available, slightly excess air should be available for the better combustion. And if we don't give the sufficient oxygen, then there will be the black smoke. This CO will take away the heat from the furnace, and you can see that heat is getting lost inside the outlet of the atmosphere, which is again the loss. So what to do? For that, we need to have 3 T's. The first T is the temperature. So you can see this is the flame nozzle, which is put inside the burner. This is oil and gas fired boiler. This is the atomizer. So if you ignite, this fuel is getting spread from here, and if you ignite this fuel with the air, so this is a combustion is getting started. So when fuel is getting burnt with the air and it is ignited, the fuel particle is which is caught up the fire, releases the heat, and again it mixes with the another particle, and this way the complete flame is getting stabilized. So complete rapid oxidation chain will be available, and this across the cone periphery you can see the flame because the fuel is burning like a vapor, and so you can see. So the fuel is like a evaporation. So fuel is burning like a evaporation. That's why the heat, the temperature sufficient enough to maintain this combustion across the symmetry is the 1 T. Sufficient time, the residence time to provide this combustion across the periphery of the furnace is also very important. And the third important part, that providing the turbulence. So means providing the secondary air or tertiary air such a way that we can have a swirling flame, and swirling flame can have a better combustion rate and better periphery across the plate, and will give the more better heat. So this turbulence is also even more important in case of suspension of the fuel particle to burn like a vapor. That's why the fuel is burning, even solid fuel is burning like a vaporations. That's why it is called fluidization in case of solid fuel. So these 3 T's are very important to maintain the combustion rate and to control the combustion. Another loss is the moisture loss or enthalpy loss, which we can't do much more because the moisture available within the ambient or moisture available within the fuel is inherent. That is very difficult to remove, and the moisture leaving out from the combustion is also taking the heat. So this is what we can do, that we can stabilize the stack temperature within the limit. So that's the advantage of 0.2-0.3% in the loss. But the unburnt loss can be controlled by providing sufficient excess air, not higher excess air, not the less air, but sufficient excess air such that the black smoke should not be from the chimney, as well as there will not be S which is getting collected from the fuel and from the furnace or from the heat recovery equipment should not have the carbon content. So this will give you the more clear idea that if we maintain oxygen near to the good combustion zone, so means above, slightly above the without oxygen level, which is a ideal combustion, stoichiometric combustion, will have a better efficient zone. If we don't give the sufficient oxygen, then there is a sudden rise in the unburnt, in the CO. Again, it's unburnt loss. And if we give the higher oxygen, then there is a sudden rise in oxygen, and so dry flue gas loss, stack loss will be higher. So we should be very near to this efficient band. That will ensure our combustion control optimization. Now, to control all these put together, we need to have a control system, and basically we should have closed loop control systems. Open loop control is not going to deliver the result what we require. For that, manual human intervention continuously required, and that is very difficult. So for that, we should have a closed loop control system, and one of the example is taken as a level, pressure, and temperature and flow. So level is very widely used. Let's take an example of drum level, where your drum level is getting controlled with sensed by the transmitter, and it is the comparator will take the error signal from the set point which is entered through the keypad. So this error signal is given, and through the controller it is conditioned and given to the control valve, such that control valve will take action to maintain the level at the desired position. Control valve open or close will give the water inside the boiler, and the level will be maintained. In this way, the level can be controlled, and so there is a closed loop action. Now that response can be available in the proportional side, but it's very difficult to adjust the error. So you can see we have given the disturbance in the form of set point change. So we have the output available with the offset, and this error is difficult to minimize with the help of only proportional. For that, we need to have integral which will reset the error. That's why it is called integral, and we can have a better response if we provide derivative also, so that rate of change of error with respect to time will be minimized. So we can have a better output and better settling time available for the response, and so that better control can be feasible. Now, to more dwell on the control side, let's start with the drum level control. So the drum level control widely use the 3-element control. Why? I will say right now. The single element control is only the level measurement. So this level is basically, as you know, P equal to H rho G. Pressure is equal to height multiplied by rho. Rho is your density, and into gravity. Rho and G are constant, so pressure is directly proportional to the height or level. So this pressure, which is getting sensed by the differential pressure transmitter, gives the command to the controller, and controller will give the output action to the feed water valve, control valve, or the feed water VFD, pump VFD, to regulate the flow such that level can be maintained. The trick here is that this is only sensing the level. There can be the false level reading also due to the shrinking and swelling effect. So where the load fluctuations are higher and the level sensings are not capable enough to detect that, that is called sudden rising in the steam demand, sudden dropping in the steam demand. So there is a drum steam space is getting swell. This effect cannot be recognized in the single element control. To act on that for the load variation fluctuation, we need to have feed forward control actions with the steam flow. Steam flow is getting corrected in feed forward manner with the controller, and the feed water flow also can be taken parallelly, and all put together. If we give the control element the desired action, the set point will be achieved in a good manner, and we can have a desired response. So in P&ID diagram, we can see in more detail where steam flow is getting sensed to the flow meter. In the feed forward action with the multiplication, some factor will be taken here, and the level input is taken from the tank, and the feed water flow is also taken in advance, such that the corrective action for the control valve or the VFD of the feed water flow pump will be regulated in more useful manner, and less effect of the shrinking and swelling effect will be available. Now, to control all these parameters, we can have analog control systems or can we have a digital control system. So analog control systems is combination of operational amplifier, and digital control system is a microprocessor based, or it can be a PLC or can be DCS. So the analog control systems can be seen like that. It is a the electronic people can correlate in the very easily that transmitter conditioned signal available to the input of the operational amplifier, such that the output action is to regulate the manipulated variable such that the control will be available. So this will act like a comparator. So the operational amplifier, all the instrumentation amplifier, and this is the analog control system. But this is having a limitations to have a faster response or linear output feasibility. For that, the better response per se and better control strategy, digital control system is always better. And digital control system is a combination of microprocessor and the devices like ADC, analog to digital conversion, and digital to analog conversion for the output taking. And microprocessor devices having inbuilt programming facility where you can give the set point remotely or by the set point or by the programming devices also, and you can modify the program for the respective control strategy and respective performance of the system behavior also. Now, just I would like to give the more glimpse on the PLC point of view. So this is one of the digital control systems very widely used, and it is invented to overcome erstwhile the relay logic based logic. And so relay logic was actually we were used to prepare a relay wiring diagram in the panel and to have a fixed set of strategy available for that kind of structure. To overcome that relay based logic is defined into the programmable logic controller, where you can have a similar kind of functionality available, but in the user configuration manner and more flexible, where you can have your fixed IO can be settable for any kind of applications where you can change later on also. So the PLC is a combination of input output module, which is the interface to the process, then CPU, which is a controller, which comprises of communication port as well as programming memory, data memory, and the power supply, and the programming devices like keyboard or a monitor, where you can see the output parameter, or you can see the set point entry, or you can give the entry and you can download the program to the controller also. Now, the basic function of the PLC, before going to that, just I would like to show some actual constructions from how the PLC actually fit into the room or maybe in the control panel, where your motherboard panel will be there. In this motherboard panel, your power supply card, then your CPU card, and then your IOS interface will be fit inside this, and it will be directly mounted on the motherboard, where your communications will be happening through this IOS as well as SMPS as well as CPU, and it will be online, and where you can connect your laptop directly to download the program. Now, how the PLC works? So PLC is basically takes the input, scans the input, then modifies the output based on the program written inside the CPU memory, takes the data from the CPU data memory. So this is the complete sequence which is follows, and continuously this sequence getting followed. So as I said, the PLC is abbreviated from the relay logic. So simple ladder diagram is the simple language for the PLC, where you can see your DI, digital input and digital output, analog input and analog output is just getting texted in the form of ladder rung. Here, if you have a better understanding of the languages and all that, and better programming per se, you can define the functional block diagram also. So where your AND logic, your OR logic, or addition, subtraction, all these blocks are put together, and you can write the structure, and that is called functional block diagram. Another useful tools is the structured text, like your programming language, where you can write your program in the form of structured text, as well as the instruction list also. Now, if you have more complex programs, more complex logic, you can use the combination of that is called sequential flowchart, where you can write a complex program algorithm with the combination of all of this, and you can define your programming of the PLC also. Now, on top of that, we can have more advanced control like DCS control, and which is again the part of, you can say, more advanced form of controlling strategy, where you can have your local control as well as centralized control can be available. And this distributed control is very widely used combination with the local and centralized control. Now, how it is advantageous, so which you can see that your centralized control can be PLC or can be microprocessor, which will be controlling the parameter and modulating your output to control your output signal. This, I will just give you the example of typical boiler, how the open loop control, where your manual human intervention is always required to control the parameter, to control the pressure. He adjusts the feeding, he adjusts the temperature for the temperature control, he adjusts the parameter. So this is the manual control, and it will not suffice the dynamic response. Now, on top of that, if we can have PLC based local control or like a controller inbuilt available for respective parameter, which will be having some good control above the open loop control. But if we can have a distributed control, which is centralized, will have a better justification in terms of dynamic response and better performance and better efficiency. Now, so if I go into the more construction point of view for the DCS side, so DCS is taking the individual field control systems, talking to the output signals in form of Modbus communication single common bus bar, which will be communicated to the operating stations where your data or SCADA is installed inside the computer. So these are the operating stations, which are the computer having the better representation of the controls of the boiler process, where you can easily modify your set point, configure that, and control the parameter. So the advantages of the DCS is that in spite of your local controller is getting failed, the complete boiler house control is not disturbed. It is the complete boiler house control is on. There is a one controller is getting failed, there you can take corrective action, can replace that and can troubleshoot that, but rest of the controls are operational. Also, redundancy can be available where you can have two computers, you can have two CPUs, and the IOs can be available as a redundant. So one channel is getting failed, second channel automatically overrides the control. Again, as I said, the representations of the SCADA and the interface, the machine interface and screens are so easily understood that you can very easily configure the parameter and control the parameter. So this is the typical constructions of the DCS system, which is comprising of CPUs, IOs, operating stations, and the communication bus. Now, how the centralized control system looks, you can say. So this is the typical controls available from, which is a computer control for the one of the typical DCS for the boiler house control, where you can see it's a solid fuel control where the furnace temperature is around 1045. The draft pressure, you can see it's controlled near to 0 mm water column, which is the ideal scenario. So draft is actually control between the FD and the ID, and which is balanced out at the furnace, middle section of the furnace. The drum level control, the pressure control, and the oxygen control. So all these parameters simultaneously put together, and you can have a better representation. So one can easily understand, any layman can easily understand, can modify the set point and can well verse with the boiler control. So how to optimize further on that? So after this, all this control philosophy available within the necessity and within the permissions in our boiler house, now we can optimize all these things put together for the resultant what we require for the combustion controls. And so combustion control is basically the excess air control or auto trimming, as well as the air to fuel regulation based on pressure. I will come one by one on this. The excess air regulations, as I said, is the control to optimize the heat loss. Otherwise, if we give the more excess air, then it is a meaning that we are losing in form of heat. This heat is getting escaped from the chimney in the form of high fuel is getting burned. So what to do for that? So we need to have the excess air near to the 10 to 25% in case of oil and gas fired boiler, and in case of solid fuel boiler, 30 to 50%. If we provide this efficient band always, and if we have a tighter control, we will be having the highest efficiency and highest control possible for the boiler. So what to do for that? So we need to have oxygen trim, and oxygen trim can be achieved with the help of oxygen analyzer put outside the furnace, which is sensing the oxygen percentage from the combustion outlet and regulates the FD, air inlet, such a way that the tighter air control is always available. And what to do with the pressure control? So the pressure control is the air to fuel cross limiting always. Why? That air should be always leading above the fuel to avoid any unsafe incident. I shown you the mimic. That mimic displays all the critical parameter which is required to operate the boiler in the efficient or safe zone. There are recent cases in couple of years. There are boiler blast scenario in many of the few of the cases where somehow the control cannot be operated in the way it should be required to be capture the dynamic behavior, dynamic response. So all this put together, we can avoid this hazardous situation and unsafe condition. So for that, if we keep in mind that based on demand signal, pressure and flow, the air should be always leading to the fuel. Though it's a tighter control, we should be keeping the tighter control for the auto trim point of view, but we should be ensuring that air should be sufficiently enough available to control the combustions and have a safe combustion in place. That's why it is called cross limiting. Draft control is based on draft pressure, which I said it's like a PID based control, and you can put a lookup table for your feeding as well as your FD, such that it can have a response in better way. But draft in respect to the maintaining the balanced draft near to the 0 mm control, 0 mm draft pressure is our prime objective for the safety as well as the efficiency. If we have a positive draft, it's indication that FD is delivering more and there is a chances of backfire. So the tighter draft control is always ensuring the safe and efficient operation. Apart from that, we need to have the blowdown TDS control. So the TDS is basically sensed in the form of resistance. So the silica level, which is sensed in the form of resistance. So actually the silica is the inverse of resistance and which is getting sensed, and we need to control the TDS at the optimum level. For the saturated boiler, it's a 3500 ppm. So for this TDS control, we can put a control valve with the TDS sensor, which is sensing the TDS outside outlet of the boiler drum and acting the control valve based on TDS level, and then it will give the precise TDS control, and we'll have an advantage that we can maintain the process pressure within the safe limit. If the TDS blowdown control is not available, the operator need to give the blowdown manually, and in this scenario, he need to always look upon the steam pressure and the pump, feed water pump is running. Now to save from this, we need to have automatic blowdown control based on TDS, bottom blowdown TDS, and it will ensure that process pressure is not getting fluctuated. However, we are maintaining the TDS in the optimum limit so that we are not draining hot water from the blowdown pit, and we are losing in form of saving the heat by maintaining the blowdown TDS near to the set point. Now, all this put together, what to be the next level for the now the Internet of Things and IoT and Industry 4 standards. So the boiler house is also up. Boiler house instrumentation is now up to that level. So you can see our prime objective have the online connectivity for the boiler house to ensure that connectivity with the local control systems and the connectivity with the server for the diagnosis purposes, for the data analysis purposes, and that will give the idea that we are playing safe in case of efficiency and environment, and the safe operation is taking place. And at the end, we are ensuring that we are reducing our energy bill, fuel bill, and utility bill by maintaining the highest efficiency. So I would just like to draw your attention to this the last slide which I presented. So you can correlate that how the online measurement is useful. So this is the live running thermic fluid heater. Okay, so you can see the oxygen, the draft pressure, the efficiency, and the heat output. Similarly, the fuel total. So all these things can be, and efficiency can be seen. The trends can be visualized. So this is the online. So this the way it gives us the idea how to optimize and what are the level of boiler operations, whether it is near to the rated, whether it is a safe zone, efficient zone, or further anything need to be done, will give the more interactive picture, more diagnostic picture, and which we can control with the help of instrumentation control available in the boiler house. I think this is it from me, and I would like to encourage you for the any questions or any doubt so that we can discuss.
Okay. Now platform to open for all participants. Please ask the question, whatever you have.
I think there are few questions listed in the chat box.
Yeah.
Let me just read out the question. There was a question from DV Jani. How to control water wall temperature in the boiler? That is the first question.
Dr. Jani, the water wall temperature, actually the water wall is connected with the water, connected to the incomer to the drum. So the water wall temperature is outside is export to the furnace. Inside is actually the taken in the measurement in the form of water flow, which is actually the steam is getting generated in the form of drum. So attenuated temperature control, which is a superheater steam temperature control, and all that will having a proper firing rate control. Look up with that. We'll have a better combustions delivering, and the water wall temperature. Actually, the water wall temperature is need to be maintained in such a way that there should be sufficient heat transfer, and it should be it should be in the radiative zone. If you see it is the water wall membrane is exposed to the combustion side, the furnace side. So that temperature from the if the is very near to the combustion zone, it can be varying from 800 degree. And if it is very near to the combustion zone, so it can go up to the 1000 degree also, 1200 degree also. Based on that, if we go further away from the combustion side, that temperature goes in the tune of 600 degree or maybe 550 degree. That is above the steam temperature. So that rate is itself is getting controlled based on the steam outlet temperature, which is limited with the help of air to fuel regulation. So in the boiler house control per se, the water wall temperature independently doesn't play any significance, but it is getting taken care with the help of steam temperature control and the furnace temperature control.
Okay, the next question is from Rakesh Patel. Is any one electronic instrument to control boiler pressure and water level, just like mechanical controller, high pressure and low water HV?
Yeah, there are dedicated single loop controllers are available. Various kinds of from the system integrator or from the manufacturer.
Okay, sir. Means, sir, this is a replacement of a water level indicator and pressure gauge.
Actually, see, that's the vital role getting played by the instrumentation engineer. So means I would like to elaborate that you would like to say that analog device which is getting measured by the human interference, you want to replace with the simple digital measurement device first, correct? So
okay.
Yeah, so that actually boils down with the putting the right instruments. So first you need to start with the what kind of steam temperature, steam pressure transmitter what you require. Basically it's a saturated, then you can go with the 0 to 40 bar gauge. Then that measurement coupled with some microprocessor based controller which is directly taking this 4 to 20 milliampere from the steam pressure transmitter, and then this microprocessor based device is displaying the temperature. Then you can have this device throwing the data to your central data central control systems or central monitoring systems. That is also can be feasible with this device. So you need to work upon what kind of cost available with you, what kind of automation you need to incorporate with that. So that's a very safe plan need to be done. However, you can think one more option, that there will be control systems will be available inside the boiler house. If there are spare IOs are available, spare input output, you can directly take that input into that spare channel. That will be very useful also without investing more.
Okay, sir. Thank you very much. Thank you.
Yep.
Sir, next question is from Kaushika Patel, ma'am. Do suggest the good free software tools for analysis of process parameters.
Free software. Basically, the free words, we don't go into the free words. Basically, the things available in the industry is always what we try to say, build the solutions around our requirement and our necessity. So there are software tools for the process parameters. So when we were in the academic and all that, at that time we used to have MATLAB, Simulink, then NI, all that things we will use to analyze for our purpose. Nowadays, I think based on the requirement and the advancement and all that, all these things are available, and you can vary in the academic per se. You can utilize in form of analysis per se, performance analysis per se. But that plays a very vital role, that how much dynamic behavior you would like to incorporate. So these are the tools are very efficient in terms of theoretical per se, but the dynamic at some extent need to be simulated into the real atmosphere, real industry atmosphere. That's the only catch here.
Sir, next question is from Huzafia, ma'am. Is there time lag of input and signal sensor to output command? Also, there is a loss of data during transfer.
Yeah. So the time lag, to overcome on the time lag and all that, that's the improvement on the time constant sides can be done for the any process industry. So I would like to elaborate, give the more detail in terms of this question. So that time lag, any instruments, for example, let's take a temperature measurement. So the temperature measurement, for the faster response and better stability and the better catching of the output signal, we need to have the temperature with thermocouple, which plate with always inserted with the thermo valve, and that time constant can be nullified such that we can have a linear response. But here the idea is that the time lag which is taken, it's not in the tune of, you can say, millisecond also, but the process change itself, it's delayed. For example, that time change will not be so faster in the boiler such that you can have every millisecond your temperature is changing. It's so the instruments is such a way that the millisecond response is good enough for all these processes in the terms of boiler house. That faster processes and all that which is behaving in terms of microsecond, all that, I think it's not viable in any kind of industry, because the processor is fast enough. Processor can scan any PLC or any DCS nowadays, can scan in a millisecond all the channels. Okay, so the processor is capable enough to scan. The device is also able to measure. The change in the physiological variable is sufficient enough to measure with respect to the way the process takes the time to change.
Thank you, sir, for this information.
Okay. So I think all queries are covered by our expert. So thank you so much, sir. I
Thank you all.
request
Thank you all.
I
Thank you, being a
request
better
all
audience.
parties.
Yeah.
Okay, I request all participants to fill the feedback form and mark the attendance in the given link. Okay, so that we can circulate the certificate for the participation. Okay. Thank you so much, sir. Now it is my pleasure to propose vote of thanks for this event. I would like to thank Principal BVM, Dr. I.N. Patel sir, and HOD EC Department BVM to permit us for this virtual technical talk for students. I would like to thank Engineer Pratap Maikwan sir, today's expert, for delivering such an informative session with a very basic terms, so all students with different branches can understood easily. I would like to thank all those who have given support directly and indirectly to make this event success. I would like to thank participants for attending the session sincerely. On top of that, I am very thankful to my dear student coordinator Vedant Dokania, third year EC department, for arranging all the necessary things with a very short notice. Thank you so much.
Thank you all.
Thank you, sir. So I conclude the session. Okay, and thank you all for participation. Thank you so much, sir.